Hello everyone and welcome to this primer tutorial on digital and wireless communication systems. My name is Mohammed Safa, and in this tutorial I want to explain to you how digital and wireless communication systems work intuitively using MATLAB projects. This tutorial is aimed at people with little or no background knowledge on digital communication systems. However, anyone who is interested in the subject can see the tutorial and hopefully can acquire a higher level idea on how such systems might work. We will implement a communication system. From the transmitter algorithm, we will transmit the signal wirelessly using the acoustic channel. We will receive the signal and do the receiver algorithm, and finally decode and see the final received data. Hopefully this will motivate you to go and read and study the subject more rigorously and can try to have a deeper understanding on the material. So let's start and see the structure of the tutorial. The tutorial is structured as follows. First, we will have a brief look at analog communication. Then we will see the general architecture of any digital or wireless communication system. Then we will see how we will implement our system. Then we will have a look at the transmitter parts and the processing that are happening in the transmitter. Then we will see the receiver parts and the processing that are happening in the receiver. Then we'll have a look at the code and its structure. Then I will show you a demonstration on how to transmit the signal wirelessly and record it on MATLAB. Then the conclusion, and finally recommended introductory reading related to the subject. First, analog communication. Here, as we can see, we have an analog signal, which is a 400 Hz tone. This is its spectrum. We can modulate this signal on a carrier, specifically on the amplitude of a carrier, as follow. And we will have the following spectrum. Here we can see the carrier on the middle and the double sideband of our modulation. This is called amplitude modulation, or AM, which is simply we can modulate our input signal on the amplitude of the carrier as follow, as we can see. And the receiver can simply receive the signal by extracting it from the amplitude. There are other analog modulation schemes that change the frequency of the carrier or phase of the carrier, which is called FM and AM. And hopefully you have an idea about these subjects. We will focus on digital communication systems, which can have the following general structure. So any digital communication system can have a baseband processing, then digital to analog conversion, and some RF chain, and finally the signal is transmitted through the antenna. At the receiver parts, we have the receiving antenna, the RF chain, also the analog to digital converter, and some baseband processing. This is a general structure of any digital or wireless communication system. So let's have an idea on what are inside those RF chain. So for example, at the transmitter, there might happening upconversion and power amplification. At the receiver, we can have low noise amplification and downconversion. And this is a general presentation. For example, we might have some kind of filters or other kind of RF circuits at the RF chain in the transmitter or in the receiver. But how we will implement our digital communication system? We want to abstract the RF parts. So we don't want to use any other hardware. We want only to use our computer to do the transmitting and the receiving parts. So this is how we will implement it. We will have some input data. We will do the baseband processing. which consists basically of modulation and pulse shaping and so on. We will convert then the signal to some kind of carrier frequency. Then we will save it as a sound file, as a wave file, which is basically can be considered the digital to analog conversion. At the receiver, we will record the signal from MATLAB, and we'll do the down conversion, convert it to baseband again, and do the baseband signal processing like match filtering, synchronization, channel estimation, and so on. And finally, we can have our output data. So let's walk through each part of our system. First, this is Claude Shannon. He has a significant contribution to the field of information theory, and he is considered the founder of the age of digital communication. So you should know him and see his biography. This is also Maxwell. He has also a significant contribution to the field of electricity and magnetism, and also some other fields. So we will use the images of these two great people as an input data and use them as the transmitter part. So first we will reshape the image to the required size, convert it to black and white, then convert it to a binary image. This is basically zeros and one. Each pixel is either 0 or 1. Then we will randomize the image using interleaving. This is to give it some kind of robustness against noise. And the error pixels can be distributed randomly and does not affect how we can interpret the image that much. And finally, this randomized pixel will be converted to a vector and will be used as an input data at the transmitter. Then we will have to do a modulation. There are two main modulation schemes in digital communication, binary BSK and QPSK. In binary BSK, we simply convert the input data, the ones and zeros, to some sample at the constellation diagram, specifically at the I-axis of the constellation diagram. So for example, if we have 1, we can convert it to a 1, or if we have 0, we can convert it to a -1 on the I-axis of our constellation diagram. This axis is considered the I-axis, and this is considered the Q-axis. And IQ representation of baseband signal is very famous, and you will see it everywhere. If we have QPSK, we can take two input data together and map it to a point on the constellation diagram. For example, if we have 1, 1, we can map it to this point, which is 1 on the I and 1 on the Q. If we have 0, 0, we can map it to this point, and so on. So each point on this constellation diagram is considered as a complex symbol. For example, this is 1 plus j, this is -1 minus j, and so on. And this is considered the complex modulated symbols that will be used at the baseband processing. Under this implementation, we will use QPSK to implement or to modulate our input data. And we will use the I-axis to modulate, or in other words, we'll use the first bit to modulate the first image and the second bit to modulate the second image. So, or we'll use the I to modulate the first image and the Q to modulate the other image. It's both mean the same thing. And finally, these images, these complex symbols will be used in the further processing. So we have to structure our data for synchronization and channel estimation. So for example, in the beginning of our signal, we use some pilots for frame synchronization. and then we use some pilots for channel estimation, and we put the first frame of our input signal, then another pilot for channel estimation, then another part of our input signal, and so on. The pilot for synchronization is used so we can know where our signal starts, and the pilot for symbol or for channel estimation we can be used to compensate the effects of the channel at the receiver. After structuring our data, we should both shape our symbols. So for example, let's assume that this is the real parts of our symbols. We have 1 and we have 0, and this is the symbol duration. We want to convert it to some kind of signal. We can send it like that. So this is the job of the pulse shaping. This pulse is called square root raised cosine pulse. This is used famous pulse in digital communication, and we'll use it for pulse shaping. The pulse shaping operation is done basically using the convolution between the impulses and our pulse shape signal. The convolution is the most important operation in signal processing, and you should always remember it. And this is one of the most important operation. So after that, we will get the pulse-shaped signal like that. We notice that we have two peaks at our corresponding to our two symbols. So the receiver can also convolve the received signal with the pulse shape that was used at the transmitter to get the final received signal. And here we can see that we have here 1 and here -1, corresponding to the two transmitted symbols, 1 and -1. This is simply how pulse shaping is done. This illustrates the relationship between the bandwidth and the symbol duration. So as we can see, increasing the bandwidth reduces the symbol duration, or in other words, increasing the rate. Here is another factor called the roll-off factor. It's associated with the pulse shaping signal. And this is generally this is illustrate in general what is the relationship between the bandwidth and the symbol duration. And you should know intuitively that many systems tries to increase the bandwidth to increase the data rates. So to increase the bandwidth, many systems go up in the frequency, and always you can see in any new generation we try to go up to a higher frequency so we can have a more bandwidth to use, or in other words, we can have a more data rate. And there is other approach to increase the data rate, which is increasing the spectral efficiency. But this is advanced topic and we will not talk about that. Here we can see the baseband spectrum of our signal. This is the signal at baseband. This is the bandwidth which is set by us. Then we convert it to passband by multiply it by the complex sinusoid. And we will have a complex signal, but we cannot transmit a complex signal. So what we will do, we will take the real parts after that, so we can get the final real signal that will save as a sound file. Here we can see that the I and the Q parts correspond to cosine and sine. So the information of our constellation diagram is preserved, and the cosine and the sine are orthogonal signal. So at the receiver, we can extract the baseband symbols again. So this is the passband signal. Here we have a passband bandwidth of 3 kHz, which is set by us, a carrier frequency of 18 kHz, also set by us, and a sampling frequency of 44,100 Hz, which is the standard audio sampling frequency. Because we have this sampling frequency, we cannot see any frequency more than half of that, which is approximately 22. And this is an important note about the relation between the sampling frequency and the frequency components that we can see. So I will demonstrate to you how we can record the signal at the MATLAB later for receiver processing. But here let's assume that we have the following received signal, and this is its spectrum. So we can notice that the signal is attenuated, it has some distortion, and it's also centered around the carrier frequency that we used. First thing we do, we convert the following signal to baseband again, and this is done by multiplying it by a complex sinusoid. So after multiplication and analytically doing the math, we will get the following result. So first we'll preserve the I and the Q components. This is the baseband symbols that we started with. We have some other doubled carrier frequency components, and this can be seen here. So this is the baseband signal that we started with, which is simply this, and this is corresponding to the carrier frequency components. So because we have a fixed sampling frequency, we cannot see any frequency more than approximately 22 kHz. Because double the carrier frequency will result to a 36 kHz. So this frequency will be translated to a mirror frequency or an alias frequency less the sampling frequency. And this can be calculated from here, and we can notice that it results to 8100 Hz, which is basically this. So it's important to keep in mind that because we have a fixed sampling frequency, we cannot see any frequency more than half the sampling frequency, which is basically here. At any frequency more than that, we will have an alias of it lower than half the sampling frequency. And here we can see finally that we preserved the I and the Q components. This is the complex symbols that we started with at the transmitter, and we will do next the match filtering. Match filtering is done simply by convolving the received signal with the pulse shaping function, and we will get the following baseband signal. Here we can see that the interference is suppressed, and we only have the baseband signal, which consists of the I and the Q components we started with at the transmitter. Then we will do the synchronization. Synchronization is done by correlating the received signal with the pilots, the synchronization pilots that was used in the transmitter. And when the pilots align with the pilots in the signal, we get a peak. So here we can see where the signal actually starts, and we can start the processing according to that. Then we have the channel estimation. So after sampling each frame, we do the channel estimation. The channel estimation is done as follows. So we transmit first unknown samples, and we see it at the receiver, and according to it we know how the channel affected the received data. For example, if we receive it as 1, we know that there is no effect, and this is the received symbol data. And if we receive it as 0.25, we know that this is the effect of the channel, because we already sent 1, we know that. So we compensate this effect from the received symbols, and we get our symbols. We can, instead of sending just simple, just one channel estimation sample, we can send many samples, and we can average them to get the effect of the channel. This is basically what we did in the implementation. So after doing the downconversion, synchronization, and receiving or sampling the signal and doing the compensation of the channel, we will get the following example constellation. So as you remember, we sent points here on 1 1, minus 1 1, minus 1 minus 1, and so on, and we receive this noisy constellation. What the receiver do? According to the position of the symbol, it decides what data was transmitted. For example, if the symbol is in this quarter, it will decide that the data that was transmitted is 1 1. If the symbol is in this quarter, it will decide that it is 0 0. Here it is 1 0, and here it is 0 1, and so on. So according to the position of the received sample, the receiver will decide or will make a decision on what was transmitted. And assuming that each sample is equally likely, this is called the maximum likelihood detection, and this gives us the maximum or the optimum decision boundaries. So in the end, this is what we transmitted, and this is what the image that was received. And as we can see, there is some error pixels, but we can see or we can recognize the image perfectly fine. So next, let's have a look at the code and its structure. So in this video, I will show you the codes and the various part of the code. So in the beginning, you should note that I'm using an older version of MATLAB, but adapting the code to any newer version should be simple and straightforward, and you can do it. So in the beginning, the code is structured to various sections. Each sections do some functionality. So here we have the system's parameter. Notice we have the sampling frequency or sampling rate. This is 44100, which is a standard audio sampling frequency. And you should make sure from your device that it supports this sampling frequency, and most of the device does, and even support a higher sampling frequency. This is the carrier frequency, and it's also set by us. We can change it how we like, but we should keep in mind that we can not use a frequency near half the sampling rate, because as I said previously, if we have this sampling rate, the maximum frequency that we can see or the system can see is half of that. And you should keep some overhead for the bandwidth also. This is called the roll-off factor. We are setting it to half. This factor is related to the pulse shaping function. It's control how the function is separated in the bandwidth, and you can see the relation between the bandwidth and the sampling symbol duration in the lecture, as we saw it before. This is the bandwidth. This is set by us, and we can control it. Increasing the bandwidth will increase the rate or will reduce the symbol duration, and we will see this shortly. We set the bandwidth, we set the roll-off factor, and depending on that, we find the symbol duration. This is the relation that we saw it in the lecture, but you should keep in mind we are setting the pass band bandwidth, not the baseband bandwidth. So this is the bandwidth that we set it at the passband when we translate the signal in frequency, and we will see the effect of this shortly. So this is the samples per symbol. This is also determined by the sampling frequency and our symbol duration. This is the length of the pilot for synchronization, for frame synchronization, so we can know where the signal starts. This is also set by us. It's just arbitrary, you can change it This is the pilots for channel estimation, and it's also set by us. We have 10 pilots, and we find the channel for each one, and we average it to determine the estimated channel or the channel state information for the corresponding frame. This is the number of frames also set by us. This is the function to generate the pulse shaping function. We give it the parameter, the number of samples per sample duration. We specify its square roots, raised cosine function, and the roll-off vector, and it's give us a function, the pulse shaping function that we will use. Here we find the length of this pulse shaping function because we need it in the processing, and this is the average energy per bit. The other section is just download the images. We have two images as you saw them, the image of Cloud Shannon and Maxwell. We set the size or the required size, and the image will be downloaded, reshaped, converted to black and white, converted to binary, and then randomized using interleaving. And let's increase this size to see the images or the final images. So we will run this section of the code using Control and Enter. Notice this image of Maxwell and this image after interleaving. This will be converted to vector and will be used as pixels 2, the input data. This is the image of Cloud Shannon, and this is after randomization. This is also will be used as input 2 or pixels 2 to our system. You can see this function later. It's just simple function. Only take the photo or the images and do the processing and give us the pixels and the interleaving pattern. Here we find the total number of samples or symbols that we'll use later in the processing. This is we have the transmitter, and let's talk about each part briefly. Here we generate a random symbols for the pilots, the synchronization pilots. Here we generate also random symbols of 1 and -1 for the channel estimation pilots. Here we do the QPSK, but here we don't have QPSK modulation. We just this can be considered as a binary PSK modulation. We only take this data and upsample it. We add zeros by the number of samples per symbol, so we make the symbol duration, and we append it to this impulses vector, and the loop is continue until the number of pilots end. And here we see this convolution operation that we talked about, and pilot symbols will be pulse shaped symbols, and we'll use it later. Here we have the same operation but it's happened to our data. So for example, notice in the beginning of each frame we add the pilots for channel estimation, and then we modulate our signal in QPSK modulation. Notice we use in the y-axis the pixels 1 and in the q-axis pixels 2. We convert them to complex number and we append them to this vector with the symbol duration, and finally we add them to these impulses. And we do this for all the number of frames, and in the end we convolve them with pulse shaping filter to get the pulse shaped signal. Here we do some plotting. Here we append the pilot symbols. Here we plot the spectrum. Here we notice we multiply the signal by the complex sinusoids, and we take the real part as we saw, But notice here we are normalizing the complex sinusoid. So in the end, the half factor that you saw in the lecture or in the tutorial will be cancelled out. We get only q or I plus jq without the half. So this is only a normalizing factor, and this is the complex sinusoid. We also do some plotting. All these plot functions, you can see them later. They just do the plotting simply. And here we see, we save the audio file so we can use it later. And here we see the total time for the transmission. So let's start this section and see what we will get. So notice the various signals that we can get. Let's start with this one. This is the impulses according to the data that we have, and this we can consider it as the real parts of the data. We have I and Q, so this is the real part. We have some impulses corresponding to the data, 1 or -1. This is after pulse shaping. So notice how the signals or how the impulses are converted to a pulse that can be used as a signal for transmission. And this is the baseband spectrum, and this is the passband spectrum. This spectrum is 3 kilohertz, which was set by us, and this is after conversion or after multiplying by the carrier. So let's see the total transmission time. Notice it is 5.5 seconds take to transmit this data. So let's try to increase the bandwidth a little bit. For example, let's make the bandwidth 4 kilohertz. Let's run this section again. Let's run this section again. We reduced the images size, so we reduce the processing time. And let's run this section also again. So first see the impulses as we saw them before. This is the pulse-shaped signal. Notice here how the bandwidth is increased a little bit. It's now 2 kilohertz. This is the passband bandwidth that we set it. We set it to 4 kilohertz. So see how the bandwidth is increased now. And this is the signal after multiplying by the carrier. So we increase the bandwidth, so we have an intuition that it will take less time to receive the signal. So let's see. Notice it is now 4 seconds after increasing the bandwidth. So increasing the bandwidth give us a higher data rate, as we can transmit more data, or it reduces the simple duration time, which is basically the same thing. So if we instead reduce the bandwidth, for example, to 2 kilohertz, we feel, or we have an intuition, that it will take more time than 5 seconds to transmit the data. And this is what we will see. So let's the transmitter do the processing. Notice here how the bandwidth is reduced, and it will be more than 5 seconds. See, it's now 8 seconds to transmit the data. So you know now why always we try to go up in the bandwidth, or we open the frequency, and always we want to increase the bandwidth, because there is a relationship, a direct relationship between the bandwidth and the simple duration. So for now, let's keep it at uh, 3 kilohertz. Let's run this section. Let's run this section again. Let's run the transmitter algorithm. Okay, let's close those figures. So I will demonstrate to you later how we can transmit the data wirelessly. But now let's assume that the receiver received the signal perfectly. So let's uncomment this part, and this, notice how the transmitted signal will be received perfectly. And as I said, I will demonstrate later how we can transmit it wirelessly. So now let's run this part. And we are assuming that we received the signal. Notice the receiver algorithm. Here, the signal is multiplied by the complex sinusoid, but now it's negative, as you know from the tutorial. We do some plotting. This part here, do the synchronization. It's find the maximum and shift the received data according to the where is the maximum position, so we can know where the signal starts. Here we do the match filtering, also convolve the received signal with the pulse-shaped function. Here we do some plotting. So this is the demodulating or extracting the QPSK samples. Notice we loop the number of frames. In each frame, we extract the pilots, the channel estimation pilots, and the data. After that, we find the state of the channel for each of the pilots. We average them, so we can estimate the channel. And here we compensate the effect of the channel by dividing by the channel estimation. And here we append the QPSK, the received QPSK samples. And we do this for all the frames. Here we do some plotting, and here we do the decoding step. As I mentioned in the tutorial, the receiver see in which quarter the symbols are and decide if they are ones or zeros. And here it will extract each received pixel, the pixels of each images after doing the interleaving, uh, converting the randomized pixel to the corresponding pixels of the image. So let's run this section and see what will happen. So notice this is the constellation diagram. It is perfect. We don't have any noise, we don't have any errors. So those are the symbols that we transmitted, and we will receive them perfectly. Here, see that it is after match filtering. Here we have the received signal after multiplication by the carrier. Notice this is the alias frequency here because it's more than half the sampling rate. So we will have an alias image of it at this range. We mentioned it in the tutorial. Here it's after the match filtering, and let's run the last part to see the received image. So this is the received image, and we received them perfectly because we had the data perfectly without any noise or anything. So next, I will demonstrate to you how we will receive the signal wirelessly using the acoustic channel. So after completing the transmitter section, we can go ahead and start with the receiver section. And after trying receiving the data perfectly without any distortion or without using the wireless acoustic channel, here we will try to receive the data using the air, using the acoustic channel. So first we should send this sound file to some other device, for example a mobile phone, and we can play the sound and transmitted wirelessly using the wireless channel to our MATLAB code. So I have transmitted, or I have sent the audio file to my phone, and I will try to play it. So you should not recognize any sound because the frequency is 18 kilohertz, and we should not recognize any of the sound we will hear, but the receiver can receive it and can process it. So first, let's start this section of the code using Control and Enter, and after that, immediately I will start the sound. Here we can see the received signal spectrum. Here we can see the received signal around the 18 kilohertz, and we can notice how it is distorted and how it is attenuated. So for example, let's try again, but maybe using the mobile further away from the mic or the receiver. Notice how we got a very little power around this frequency. It's almost near the zero, or near the noise, because our phone was very far away from the receiver. So let's start again and do the receiver algorithm after that. So this is the received signal, and this is its spectrum. I will try to complete the receiver algorithm step. So let's run this section also. So let's see some of the figures. So this is before match filtering. This is the constellation diagram. Notice how it is very noisy, and this is the signal after match filtering. So with this constellation diagram, we can have some intuition that maybe we can recognize the images, maybe not. So let's start and run the final part to see the images. Notice we can still recognize the images. So if you squint your eyes, you can recognize the image for Shannon and Maxwell. Let's start again, and let's receive a very tiny or very small signal, very small power signal. So let's close the figures, and let's run this part again. I will put my mobile phone very far away from the mic. Notice this is the received spectrum. It's very little power around the carrier frequency that we use. Let's run the receiver algorithm. Notice the constellation diagram is very noisy. So just by seeing this constellation diagram, we can have some intuition that maybe we will not receive the images perfectly. This is after match filtering, and this is after down conversion. So you can see that the signal is very attenuated, and we can rarely see any power at the baseband. So just by simply seeing the constellation, we can have some feeling that maybe we will not receive the signals or the images perfectly this time. So let's run the final part and see. as we expected, we cannot see any figures here. We cannot recognize what's going on because the signal is very attenuated and we cannot receive the images perfectly. Let's start. Let's do a final demonstration, but let's so this is the spectrum of the received signal. Let's run the algorithm of the receiver. So this is the constellation, and we can feel that maybe we'll receive the signal or we will recognize the images at least. So let's close this. This is after match filtering. This is after down conversion, and we had a feeling that we will see the images or we will recognize the images because we had a relatively good constellation diagram. And let's make sure of our intuition. And yes, we have noise. It is not perfect, but we can see or we can recognize the images perfectly. These data literally was sent through the air, through the acoustic channel, and the receiver recorded the signal and did the receiver algorithm and get the final data, the final image. So this is literally was received through the air wirelessly, and this is, as you know, how wireless communication systems work. So let's conclude this demonstration, and let's move on to the conclusion. So in conclusion, we saw the general architecture of any digital communication system. We had an idea about the processing and the transmitter, like modulation, constellation diagram, pulse shaping, the relationship between bandwidth and symbol duration. We had a feeling of some digital signal processing, like convolution and sampling frequency, and the effect of sampling frequency. We saw the importance of synchronization at the receiver so we can know where the frame starts. We had an idea about channel estimation also, and so on. But in general, in this implementation, we only focused on implementing a primitive system without going into any details. So, for example, we did not use PLL uh, for carrier synchronization, or we did not use any advanced channel estimation scheme. We just want to use a simple thing that can illustrate the the idea. And I hope this can motivate you and can interest you in this subject, so you can go ahead and read and study the subject even more rigorously. And I hope that you will connect the dots looking backward on what you have seen in this tutorial. Moreover, MATLAB offers advanced toolbox for wireless communication and for communication in general. Can be used for testing, evaluation, and even also for implementation on hardware like FPGAs. And when you are more experienced with the subject, you can see those toolbox and see what MATLAB can offer. And finally, some suggested reading. I suggest this book for if you want to go deeper in the subject and you want to study the theoretical part more. In my opinion, this is the best introductory book. It's really well written and you can follow it easily.